All right, we're going to be continuing our study of limits from more of a graphical perspective. Okay, so let's start by just looking at a random graph that I'm going to make up. Okay, so we're not going to have like a specific function, or it's going to be a specific function, but I'm not going to write it out like with an algebraic rule. We're instead just going to have it as like a picture. Okay, so you can draw along with me this graph. So first of all, let's give ourselves a grid. And we're going to get a few key points in here. Let's say there's going to be a point right here at like 1, 1. And then maybe at like 4, 3, there's going to be an open dot. And at 4, 1, there's going to be a closed dot. And then maybe we'll have, let's do like a vertical asymptote here at 7. And then maybe a point like right about there at like 2, 2. So what I want to do is go kind of like that. And go like maybe like that. Ooh, and then let's make a hole here. Let's make a hole right here. Go like this. There we go. So this is our function. This is the graph of f of x. It's a pretty wacky looking function. Like you probably only get something that looks vaguely like this through some sort of complicated piecewise definition. Most algebraic functions don't have like all of these oddities, right? But this graph, it's the reason I made it have like all of these different properties is because I wanted to make a graph that will like sort of it will demonstrate a bunch of different things at once. Okay, so we're going to go through here, and what we're going to focus on is trying to figure out the limit of this function at different x values. And as we go through and do this, we're going to contrast that with the value of the function, like the output value of the function, so that we can learn something about how they are related to each other. Let's do it over here. So over here, we're going to have two columns. We're going to have f of x, or let's call it f of a. And then we're going to have a second column for the limit as x approaches a of f of x. So these are two different things. We can we can call them the function value or the function output value, whatever. And then this is the limit value at some number, right? So let's start with, for example, here. Actually, there's one more thing we're missing. There's one more typical type of thing I gotta stick in here. Let's put an extra point right here at x equals 5. It's at about height 2. Let's put another circle, and then let's put something like this. Okay. So let's start with that one. What's f of 5? Well, if we go to x equals 5 and we look at the function, the actual height of the dot on the graph is about here at 4, right? Let me fill in a couple more of these. So we'd say f of 5 equals 4, right? Because that's the height of this point on the graph. But if we ask what is the limit of the function as x approaches 5, that's a different thing. Because the limit of the function doesn't actually care what the value of the function is at 5. All it cares about is what the values are approaching as x gets close to 5. So all we really care about is as x approaches 5 from the left and the right, the points on the graph, what are they approaching? Well, their y coordinates are all approaching this value right here, which is about 2. Actually, it looks like it's a little more than 2. Let's just eyeball that at like 2.3 or something.
Hi, Tristan. Do you mind moving your video camera a little bit? Because it's kind of like over your work.
Oh, you should be able to move that yourself.
Oh, thank you. Thanks. Sorry about that.
Oh, no worries. That's okay. Yeah. So you have some control over like where the different windows are. The same thing with the chat. If you have the chat open, you can move that around. So if anybody out there has like multiple screens or like multiple monitors, what I like to do is have my Zoom on one and then the chat and the faces on the other one. You can also minimize that if you want to just get rid of it. You can at the top, there's different options, and there's like the sort of like the hide thumbnail video versus the like just the speaker, and then you have like a whole like tableau of different faces. You can kind of control that. Okay. All right. So, oh yeah, what do we estimate this as? This is about like 2.3 or something. I think the point here is that the limit of the function at 5 and the value of the function at 5 are not the same. At least, yeah, not the same, not at 5. Let's look at a few other examples. Let's look at 9. At 9, the limit or the value of the function doesn't even exist, right? Like there's a hole in the graph at 9, and there is no dot at all. It's just missing, right? It's not there. So we would say f of 9 equals, and then we can write DNE as an abbreviation for does not exist, or maybe undefined is another word you often see, especially when you're talking about the value of a function. So that's undefined. Let me scoot this down a little bit. But the limit of the function at 9 is defined. Limit as x approaches 9 of f of x. This is defined because it's just right here, right? It's right here. And this is about 2 by the looks of it. Okay, so that's 2. So there again, so sometimes you can have the limit exists, but the function not. Conversely, next, let's look at 4. What happens at 4? Well, if I look at 4, the actual value of the function occurs at this point right here, which is at height 1. So I can say f of 4 equals 1. But if I ask the limit as x approaches 4, now instead of identifying what actually is going on at 4, instead I would say, okay, what's happening as x gets close to 4 from the left and the right? Well, let me switch colors actually, because it's getting a bit busy here. So as we get close from the left and the right, well, from the left side, we have points on the graph coming down, approaching this height right here. From the right side, we have points on the graph coming up and approaching this height right here. So from the left side, it looks like the limit is 1. But from the right side, it looks like the limit is 3. So what do we say?
No solution?
Yeah. This limit does not exist, or we can say no solution. We could kind of break that down though, and if we wanted to be more specific here, we could say the limit from the left side of the function does exist, and that limit from the left side is 1, whereas the limit from the right side at 4 also exists, and that equals 3. But the fact that these are not equal to each other is what tells us this doesn't exist. That's one of the ways that a limit could not exist. Now we could have broken down limit from the left and the right for any of these other ones as well. So like for 5 or 9, like we could have broken it down left and right, but they would have been both equal to the same thing, right? So like at 5, for example, we could have broken down limit from the left is equal to 2.3, limit from the right is equal to 2.3. They're both equal to each other. So the overall two-sided limit, which is what it is if you don't specify, that exists and equals 2.3, right? So I didn't break that down because it wasn't that interesting, but we certainly could have done. Any questions so far?
Oh, I have a question.
Sure, Justin.
So in f of 5, why does the dot go all the way up to 4?
Why did I draw it like that?
Oh yeah.
Just because I wanted to give an example of a situation where the function value exists and the limit value exists. They both exist, but they're just not equal to each other.
Okay.
So yeah, I mean, there's just because I wanted to have an opportunity to, describe that in this example.
Sure. Okay.
Because there's no other point on this graph where that would happen.
Yeah, I also had a question. So when you do the function output value on the left, you're just focusing on like a point, but then when you're doing the limit, you're focusing on the graph more?
Yeah, actually, yeah. The function output value is like it's like the horse has blinders on, right? It's like you're only looking at one point and that's all you care about, and literally nothing else matters. It's just what happens when we plug in 4 to the function, you get 1, right? Whereas with the limit, you have to take the blinders off and look to the left and look to the right and be like, okay, now what's the context, right? What's going on in the neighborhood, right? Around x equals 4. We're coming in from this side, we're coming in from that side. And you don't actually care about what's happening at 4. If anything, it's like you take your blinders and you move them to here. And now I can only see to the left and I can only see to the right. And what actually is happening at 4 is no longer relevant. It's all about
The graph, basically. How the graph is. Okay.
Yeah.
But like for f of 9, for the other ones, you use like an actual solid point, but then for f of 9, you used a whole point on the graph, I think.
Yeah. So that's an example where there is a hole and the function isn't even defined, right? So we already saw like an example of this in an algebra. Like we looked at like log of x over x minus 1, and at x equals 1, it was undefined. There was a hole there.
Right.
Yeah, so this like totally happens in algebraic equations or functions too. Yeah, so the only difference between 5 and 9 is that like they're both holes, but with 5, the function does exist. It's just not where you're kind of expecting it to be. It exists, but it's somewhere else. Versus 9, it's just a hole and the function doesn't exist there.
So what prevents somebody from confusing, when you say the function of 5 equals 4, what prevents you from confusing the 2 points that are you're at 5?
Well, when you're looking at a graph, you want to be paying attention to whether the dots are open or closed, right? So a filled in dot means this is a point on the curve, whereas an open dot is used as sort of a boundary. It's like the graph is like getting close to this dot, but this dot is not part of the graph.
Okay.
So
Okay,
all these
thanks.
circles are like empty.
All right, thanks.
Hey, welcome. Good question. Let's look at a couple other points on this graph. So let's look next at x equals 2. We go over here to x equals 2 here and look at what's happening. Now, I didn't really draw like a dot on the graph, but one thing to keep in mind is that where the graph exists, where you see a portion of curve, you can kind of conceive of that as being made up of dots, right? Like there are infinitely many dots along this curve that are infinitely close together. And so they just form a continuous curve. Does that make sense? So there's a portion of curve here. So I might as well imagine that there is a dot there, a filled in dot. Like I could draw it there and that would be valid, right? Does that make sense?
Yeah.
So that point there at the sort of like apex of that particular portion of the curve, it exists, right? There's a point on the graph and the function value is 2. So I can write, let me scoot down here a little bit. I can write f of 2 equals 2. And then if I ask what is the limit of the function at 2, it's also 2. It's also 2, right? The same. So I want to highlight this situation right here in particular, because this is what we call continuous. F of x is continuous at x equals 2. Continuous means that the function's value exists, like the function's defined, the limit exists, and they're equal to each other. And that word continuous has that like rigorous definition, right? It has a very specific meaning in math, in calculus in particular. And that is the case at every point where the graph is just like, there's just a curve. There's nothing kind of like exciting going on, right? So like continuity occurs here. I'm gonna make it purple, right? Like I did before. Continuity occurs here, but we also have continuity here, and here, and here, and here, here, and at every other point where it's just, there's just a continuous curve. Okay. So actually the vast majority of points on this graph are like this one, where the function's output value and the limit value are equal to each other, and they both exist. And so the vast majority, like infinitely many points on this graph have that property. This is mostly continuous. There's just these specific points where weird things happen, right? Which are the ones that I've been paying attention to here. So just keep that in mind. We might spend a lot more time talking about these weird cases, but that's because they're weird. It's not because they're abundant. Does that make sense?
I have a question.
Yeah.
So f of 2 is equal to 2, right? And the limit of x is equal to 2. Like, is it like anything like, so like 2 is in the middle of like 1 and 3, and then you have to find the limits of the line that's going down to 1?
I'm not sure I understand your question. Can you try again?
So like, how did you find like the limit of 2? Like, I'm
How do we find
confused.
this?
Yeah.
Oh, sure. Okay, so yeah, so zooming in over here, right? You've got this specific point right here, right? this point right there, yeah. That point tells us f of 2 equals 2, right? But then if you look at what's going on with the graph, as you come in on the graph from the left side, from the right side or the left side here, the graph is approaching that very same point.
Oh.
So that exact same point, right? It's so it's at the same. So that's why the limit, because the limit is the whatever y coordinate the points in the graph are getting close to, right? Like over here, we had the points in the graph are coming in, approaching this point here, and that's getting close to 2.3 or whatever this was, right?
Oh, okay.
Yeah. So I mean, these are all y coordinates. Like this is a y value, and this is also a y value. The outputs of both of these things are both y values. It's just a matter of like, is this the y value that's actually being spit out by the function, or is this the y value that the function, the outputs are like approaching? You know, there's a difference between how you find that with those y values.
Could I ask something about that?
course.
So you say f of 5 equals 4, but then that's for the function output. But then for the limit, you're using a different point though.
That's right.
Shouldn't you just do f of 5 equals undefined, and then the limit of x approaches 5 is f of x equals 2.3? Like, shouldn't it be undefined and then 2.3? Shouldn't you use the same point? Or
So I see why you're saying that, and that's how it works over here at 9, right? But the thing is, if you stand back and look at that again, you could say, well, wait a minute, but f of 5 equals 4. Like, yeah, you might have this point down here where it looks like the graph is undefined, but if I actually say, if I'm not looking at this graph and say this graph is, you personify the function for a moment and think of the function as a person who you give them something and they give something back to you. If I say, here's 5, I give them the input of 5, and then the function gives me an output back, it's going to give me 4, because that's where the dot is. You know what I mean? So like, you can't get around the fact that the output of the function when you give it an input of 5 is going to be 4, because there's a dot there, you know? Like does that make sense?
yeah.
Yeah. Now, one of the things that we talk about doing sometimes is redefining functions. So sometimes, yesterday I brought up the word discontinuity, and I mentioned how this is a discontinuity here. A hole is also a type of discontinuity, but there's another name for that. It's called a removable discontinuity. I'm gonna put a little star next to this one and a little star next to this one. And these are called removable discontinuities. Kind of getting ahead of myself here. This is actually introduced in 2.3, but since you're asking, I thought it might be worth talking about. It's the reason it's called removable is because you could just redefine how the function works so that you make it continuous. Like we could say, you know what, this is dumb. Why the heck is the function being defined to equal 4 at that point? Screw that. Let's fix it. Let's remove that discontinuity and redefine it like that. And why the heck is the function undefined right here? We might as well make it defined. Let's redefine the function so that it's like that. And now this is continuous and this is continuous. Because it's like you took the hole and you just filled it in. And now it's nice and smooth. So that would require literally redefining the function, right? Like taking the way it's defined, the way it's written, and like maybe making an extra comment about it. Do you want to see what that looks like on the algebra? So take this, for example. We had yesterday this function log of x over x minus 1. And this is undefined at x equals 1, right? So this is the way it's defined for every x value other than every positive x value, because I guess it's not defined for negatives either. Every positive x value other than x equals 1. But if I wanted to redefine the function, I could make it a piecewise function like this and say, this is how it's going to be defined for x not equal to 1. But for x equal to 1, I'm specifically going to define it with a different rule. And then I could use a constant number here. I could say like at x equals 1, let's define it to equal 5 or whatever. And now I've redefined the value of the function. Now it's not undefined anymore. Now it's not undefined at x equals 1. Now it equals 5 when x equals 1. Now, if I wanted to fill in the hole, I'd have to figure out what the limit is. And I think we did that yesterday. I think we did that like numerically. Log of x over x minus 1. It does have a hole at x equals 1 over here. It's like undefined right there. See? And it's getting close to something. Now, if you do like f of 1.01 or 1.00100001, if we kind of like do this, we can see those numbers are getting close to 0.4343, kind of. I mean, that's a hard number to write down because it looks like it's probably irrational. But whatever that number is, we could define this specifically to equal that value. Let's see if I can do it. Yeah, take that number, stick it in there. And by redefining the function just at that one x value, I've now made this continuous at x equals 1 instead of having a hole. So that's kind of what that looks like. Yeah. Okay, so I'm going to put this back just for the purpose of the notes here. I don't want this to be confusing for anybody looking at this later. I'm going to put this back the way it was before. So there was a hole here, and a point there. All right. There's a question in the chat regarding quizzes. So on quizzes, I've ordered a cart of laptops. So we have like these win books. And so you guys will have access, everyone will have access to a laptop, and all you're allowed to use it for is Desmos. So you'll have Desmos on quizzes. Especially for this first quiz, I'm going to ask you to be like, probably going to ask you to do some, trying to solve a limit numerically, right? So you're going to need a calculator of some kind. So you don't have to bring a calculator. I will provide the Desmos for you. But then I also could give you something like this on the quiz where, this is something where you just have to look at the picture and tell me what the answer is. And there's no calculators involved. Like you couldn't possibly use a calculator here because I never really gave you enough. And this is it's not well defined enough to plug anything into a calculator. It's just a picture. So you might be doing this too. Go ahead.
I got a question.
Anna.
So then with that, if we were given that kind of problem on a quiz, you would have like some sort of question to go with it to know like what are we looking for, like what the answer is.
Oh yeah, for sure. Here, let me
Okay.
show you an example from a previous semester. Just a moment. Oh no, that's not the right one. Crap. No, that's chapter 3. Meant to get up chapter 2. All right, so here's an example of what that problem might look like. Okay. got all sorts of fun stuff. I probably could have just copy pasted this into the notes today and used this one, but for some reason I didn't think to do that. So I'm just drawing it all instead, but you know, that's fine. You guys are drawing along with me. I hope so. Yeah, you see what it says? So there's nice instructions here, and I've stopped doing points, so we're not going to do points anymore. But you are going to have a problem that looks like this. It tells you what to do. We've got here the function values, here the limit values, and obviously there's not going to be the same answers because we got the same sorts of issues here. Here we have a hole, here we have a hole, but the graph is over here. Here's a jump, here's a vertical asymptote. I mean, this is very similar to the graph that I just drew for you guys. It's got all the same quirks, right? So one point we haven't looked at yet in our example here is the spot where there's this vertical asymptote going on, right? Let's look at that, and then I think that'll wrap up this example.
Do you have that worksheet available? Maybe like an answer key that we could like work on.
Study from? So you guys have a set of exercises. You guys are gonna have another exercise set next week, I think. Yeah, and so you'll have a problem very similar to that on your next exercise set. So it's coming.
Okay.
I might give you that exact one that I showed you. Yes, I have it written already. So, okay. Yes. So let's see. So we want to look at what's going on here. This is a weird spot. So most of the time when you have a vertical asymptote, the function is undefined there. Not necessarily true, but in most cases that arise in like algebraic functions, it's undefined. So think of things like, 1 over x or like tangent of x. 1 over x has a vertical asymptote at 0, and it's also undefined at 0 because it's dividing by 0, right? Tangent of x has a vertical asymptote at pi over 2, and it's also undefined at pi over 2. So like most cases that arise with a vertical asymptote, it's undefined. And then when it comes to the limit at a point like that, so now I have x approaching 7 here, we can say DNE for does not exist. But technically this is technically this is correct. It is technically correct to say it does not exist. However, it is it would also be reasonable to say infinity in this case. Infinity is not a number, as I explained yesterday, but it is a direction, sort of, right? It is like, if you say the limit is infinity, that's not saying that the function ever achieves, it ever gets to infinity. It never obtains that value as an output. Instead, it's saying that it's approaching infinity. Now that is something you can do. You can't ever have a function equal infinity, but you can have it approach infinity. So infinity is a valid answer for a limit, but it's not a valid answer for a function output. So you never want to say f of something equals infinity. No, but the limit of a function could equal infinity. Does that make sense?
Yep.
I'm gonna export this. Okay. I think I want to say a few more things about that, about infinity as a possible output. Maybe we can look at some examples. Okay. I'm going to go over to Desmos for that. Let's look at tangent of x. Or no, let's not look at tangent of x, actually. Let's look at tangent of pi x. Because pi over 4x. Let's spread that out a little bit. Okay, tangent of pi over 4x, and let us look at what's going on right here at x equals 2. Okay, x equals 2. There appears to be a vertical asymptote here. Okay, now we can say limit of f of x as x approaches 2 from the left equals infinity. But that's plus infinity. Okay, because as you can see, if we approach x equals 2 from the left side, right, there's 2. If you approach from the left side, it goes up. And it's going to go up indefinitely, right? Without any boundary up above it, it goes up towards infinity, right? Phew. Now, if you look at the limit as x approaches 2 from the right, it's different, right? From the right, it approaches negative infinity. Now, in this case, if we ask for the two-sided limit, the limit of f of x as x approaches 2, not from the left or not from the right, this doesn't exist. But I wouldn't answer infinity, and neither would I answer negative infinity, because just like a jump discontinuity, the limit from the left and the limit from the right are not the same. Plus infinity and minus infinity are not the same direction, right? You can't say the limit is east if the limit from one side is east and the limit from the other side is west, right? So even though infinity, neither negative infinity nor positive infinity are numbers, we can still say that they're not the same, right? They're still different directions in a sense. So, so actually what I want to say here is just DNE. So when you have a vertical asymptote that's approaching infinity, if it's approaching different infinities, like positive versus negative on each side, we still say overall that the limit doesn't exist. Contrast this with something like, say, x over x minus 2 in parentheses squared, right? Something like this. This also has a vertical asymptote at x equals 2. I'll graph it so you can see it nicely there. Let's make that nice contrasty blue and orange. So there's there's a vertical asymptote at x equals 2. You can see that fits nicely there in that sort of narrow gap between the curves. In this case, the limit. In this case, the limit really does equal infinity. And that's plus infinity, right? Because it's the same on both sides. That makes sense? So so that's kind of the rules about how you determine whether it's valid, whether it is like correct to say that the answer is infinity, or if we turn this around, we can then say now it's negative infinity, right? It's only if you still have to consider the behavior on the left side and on the right side, right? You still have to think about both sides to be able to answer that with infinity. I think that pretty much sums up what I wanted to teach you guys about today. Let's take a look at the textbook before we wrap up here.
So are we doing 2.3 on Tuesday?
Yeah, we're gonna start 2.3 on Tuesday, and 2.3 is going to so yeah, preview. 2.2 is all about like the concept of a limit, right? So we're learning about like what is it? We're talking about vertical asymptotes. We've got like, we're practicing using notation, exploring the relationship between one-sided and two-sided limits, right? Using the graph to estimate the limit of a function, using a table of values to estimate the limit of a function. But none of these things are really a rigorous way to calculate the value of a limit or solve for a limit. None of these strategies are rigorous. None of them can tell you, oh yeah, the limit is equal to exactly this number. They're all like basically the two ways that we've approached solving limits is using a table of values to make an educated guess, or looking at a graph to make an educated guess, right? They're both still just estimates. Starting with section 2.3 on Tuesday, we're going to start learning about how you actually can find the exact value of a limit. And it's going to involve algebra. So all that algebra we were practicing on like the first day of class when we were reviewing how to like simplify expressions, all of that, we're going to start using that along with a few other limit concepts to solve some limit problems rigorously.
I have a question. Do you want us to attempt the problems on like 2.3 and like above, even though we didn't learn them? Or like if we're done with all of 2.2 homework, like chapter problems, and just wait until you teach us and then continue just like.
If you want to try working ahead, I think that would be fantastic. Yeah. Try it on your own first, and then and then that'll give you, if you start exploring it and be like, let's see, so like, let's take a look at some examples in the book and see if I can figure this out on my own first, and then Tristan will explain it later. Like, that is a great way to learn. Yeah. I want to answer Elijah's question in the chat there. So Elijah's basically asking, I think, can you give sort of more than one answer for a limit? And the answer is no. A limit, like a function, should have one and only one output. Like you never say f of 2 equals like 3 and 7, right? Like we never say that, because it violates one of the core rules of functions, which is that outputs have to be what's called well-defined. Like the output of the function has to be one number. You can't have it output two things. Same with the limit. So instead of saying that the limit is both negative and positive infinity, we just say the limit doesn't exist. Same with jump discontinuities. You can't say the limit is 3 from 3 and 7. The limit is nothing, unless you're specifically saying limit from one side or the other. And then each of those is also just one thing. Okay. Yeah. All right, folks. So we're at the end of our time. Have a great weekend. You have the you have homework to work on, but I'm going to be posting the next exercise set very soon, possibly in the next few hours. Okay. Bye, everyone.